Hey kids, we're going to talk about harmonic series today.
This is a simple harmonic series expressed by the summation of 1 over n plus 1, and is a series of values, so it's not really a function. So the summation is increasing slowly. For instance, 2 terms, a summation of 1.5, 3 terms, a summation of 1.833 repeating, and so on and so forth. So, this begs the question, what's the asymptote? There isn't one!
This is a graph of a harmonic series. As you can see, it looks like the series should eventually reach an asymptote, but it never does. The intervals by which the series increases will grow smaller and smaller with each term, but it will always be growing. Since it never reaches an asymptote, a harmonic series is considered a divergent equation.
So, where does this funky fresh series come from? Well, in the 14th century, there was this guy named Nicole Doresime who was super into math, probably because he had no friends, because his name was Nicole. In his best-selling novel, Tritactus de Configurationibus Qualitatem et Motuum, he proved that harmonic series was divergent, using the proof here. For every n that is a power of 2, there are n over 2 terms in a series between 1 over n over 2 and 1 over n. You know that each of those terms is at least 1 over n. You can prove that you can make blocks that will be equal to 1/2, and 1/2 plus 1/2 ad infinitum is always increasing.
Still don't believe us? In the 1700s, Euler came up with another proof that was slightly more elegant. He looked at groups of 3 terms. As you can see here, so we have this group that's 1, and then we have this next group that's 1/2, 1/3, 1/4, so on and so forth. So each group of 3 terms will be greater than 1 over n. So in this case, the first group is 1 over 1. The next group is greater than 1 over 2. The next group, in turn, is going to be greater than 1 over 3. And this means that it will always be increasing. So the sum of these 3 terms is going to be, h is going to be greater than the sum of these terms, group like this. So let's say we wanted to look at snowfall records, because that's the subject that's been on all of our minds lately. So once we start recording snowfalls, year 1 is going to be a world record. It's the first one. It's the most snow we've ever had. Year 2 is going to have a 1/2 chance of being a world record year. Year 3 is going to have a 1/3 chance of being a world record year, and so on and so forth. Therefore, it follows that, on average, in 2 years, you're going to have 1 1/2 world records broken, and so on and so forth. And as you do your harmonic sum out, you should be able to figure out how many times the world record should be broken over the course of n number of years. If it's broken more than this, or less than this, you can infer that there's something wrong, that some other factor is changing the number of world records broken. So let's say we look at like the mile, right? The world record for the mile has been broken many more times than a harmonic series would predict, but that's because training and nutrition and coaching has all gotten better, and so milers are getting faster and faster and faster. Is you stack dominoes off the edge of a table. You know how you can stack a domino halfway off the edge of a table?
I have done that.
Well, if you take 2 dominoes, you can stack it a little more than halfway, because the weight of the top domino holds the bottom domino on.
Physics.
Physics is pretty cool. But did you know you can actually extend dominoes indefinitely off the edge of a table?
No way.
Really? This helpful video shows how. So as you can note in this video, the blue dot represents the center of gravity. Now watch carefully as the center of gravity never shifts despite the increasing number of dominoes in the simulation.
That's pretty cool stuff. So what does that have to do with harmonic motion?
Well, it can be modeled by the harmonic series, because the first domino is halfway off the table, the next domino is only a third of the way, and the next domino is a fourth, etc., etc., just like a harmonic series.
Cool. That's not how. Maybe y'all have been confused with some of the vocab we've been using during this presentation. So we've got a super helpful list of vocab so that you know what we're talking about. So a divergent equation is when an equation doesn't have an asymptote. And that's what our harmonic series is, because as we've proven, it turns out to be an infinitely repeating sum of 1/2. And so you might be saying, well, what's a series? Well, a series is the sum of a sequence. So it's points that are unrelated, but that form patterns when you put them together. And so that's like because you know that the harmonic series is 1/1 plus 1/2 plus 1/3 and so on and so on. So they form a pattern, but they're not related to each other.
And finally, we have a harmonic, which is an overtone accompanying a fundamental tone. So an integer multiple of a given frequency. So 660 hertz and 440 hertz, the harmonic of 220 hertz, which is really important with our last application of harmonics, which is the harmonics you might have heard of before, also known as "Hey man, I don't even like dominoes," or please watch this following expression of our demonstration of harmonic overtones.
Okay.
So I was hoping you could teach me about how harmonics work with music.
Sure. Oh, hey, John. We're just doing music stuff. That's
really?
what you do. Yeah, we're doing harmonics.
So I was hoping maybe you can play a harmonic series on the piano.
Okay, well, for C, the first harmonic is just an octave up, so it's the next C. So it goes. And then the one after that is that G, so it's C, C, G. And then after that, you go back to your C, so. And then following that is your E.
Wow. Thanks, Shep. That sounds really nice.
And that's how you apply harmonics in real life.
Right, because an octave is just a doubling of the wavelength, or a half when you go higher. And the other harmonic intervals are all on the same harmonic sequence, which can be calculated using a simple harmonic expression.
So, like, in terms of applying overtones to harmonic series, it's if you divide a string into the fraction given by a point in the harmonic series, you'll reach the next overtone of that harmonic, of the note. So, like, if your first note is, say, like an A, and then you take your A string that's tightened to a certain length and you divide it in half, so you have two strings that now have different tensions, that will be the first overtone, which is just going to be the next A octave up.
And now you can play the violin. You're welcome. We'd also like to thank all sorts of great math sites for helping us do the research here.
Woo!